So when we worked on this handout, we saw that if you have a function of more than one variable, you can write down integrals over each variable. Since we're most of the time going to be working with functions of two variables, that means you can have double integrals. So this is a double integral. And geometrically speaking, it gives us the volume under the graph. So we do need some bounds to describe the region down in the xy plane, right? This rectangle down in the xy plane that our volume sits under, right? There's this curved sort of, it's rectangular in the xy plane. The sides are vertical, but the top of it can have some crazy shape depending on what the formula for the function is. But asking about this volume gives us the idea of a double integral, which looks like this, right? Okay, so in general, if you have a function and some rectangle down in the xy plane, then the double integral, that's just the integral in the x direction. Inside the integral in the x direction is an integral in the y direction, and the integrand is just the function. And we saw with our example in the handout how to evaluate this. You just calculate the integral on the inside, where you treat x as a constant and y as the variable, and then you do the integral on the outside, right? By the time you get to the integral on the outside, the y's are gone because you've done a definite integral with respect to y, and so for the outside integral, it's a single variable integral by the time you get there. We came up with this double integral because it gives the volume beneath the graph of f. So that is to say the volume under the graph but above this rectangle in the xy plane. Geometrically speaking, it seems like, right, we came up with this expression by slicing the region in the xy plane into vertical cross sections, and then once we figured out the integral along a vertical cross section, we added all the cross sections together by doing an integral in the x direction. That's why these dy and dx came out in this direction. But it seems like it would have worked just as well the other way, right? If we sliced this horizontally, we would have to integrate along each cross section would be an x integral because we're going from the left to the right. And then adding up the cross sections would be a y integral. So that would give us an x integral on the inside and a y integral on the outside. That would be like this. And it seems like that should be the same thing because intuitively it seems that both of these should just give you the volume under the graph. Right. One thing to be careful about is if you put the y integral on the outside, you have to be sure to put the y bounds on the outside. Right. This notation that we use for expressing the bounds of our integrals doesn't tell you explicitly what variable the bounds are for. The only way to know that from the notation is that the outside bounds go with the outside differential, and the inside bounds go with the inside differential. So do be careful about that when you're writing down double integrals. Okay, just to have an example, let's calculate the integral of this function f of xy e to the x plus 2y on this rectangle from 0 to 2 in the x direction and 0 to 1 in the y direction. So we could split this up, or we could write this in either way, either with the x on the inside and the y on the outside, or the y on the inside and the x on the outside. So let's set both of those up. So if we put the x on the outside, our x bounds are from 0 to 2. And then putting the y on the inside, our y bounds are from 0 to 1. And our integrand is e to the x plus 2y. Okay. On the other hand, if we put the x integral on the inside and the y integral on the outside, like so, then our y bounds go on the outside integral, so 0 to 1 in the y direction, and our x bounds go on the inside integral, 0 to 2 in the x direction. And the integrand is still the same, right? The function we're integrating is still e to the x plus 2y. All right, let's go ahead and evaluate these. So let's do the one on the left first. So treating x like a constant and y like the variable. So the x integral is still waiting for us. We're working on the integral on the inside. So antiderivative of this, treating y like the variable, we get 1/2 e to the x plus 2y. Okay, now we have to plug in our bounds like this. So that gives us integral from 0 to 2. This 1/2 we can slide outside, all the way outside like this. Okay, now we need to plug in our bounds, and remember these are y bounds. So when we plug 1 in for y, we get e to the x plus 2 minus, and then when we plug in 0 for our y bound, we get e to the x. Like this. Now we can do our x integral. So 1/2, and then an antiderivative, that's going to be e to the x plus 2 minus e to the x. So that antiderivative is straightforward. And evaluate from 0 to 2. When we do this, we get 1/2. Okay, now plugging in our 2, we get e to the 4th minus e squared minus, and now plug in 0, we get e squared minus e to the 0, which is 1. Okay, so we get 1/2. Let's see, we have e to the 4th. Here's minus 2e squared plus 1. Okay, so that's doing our first integral. Let's see what happens if we do our second integral. So this time the y integral is going to be waiting for us after we do the x integral. When we do the x integral, right, our antiderivative treating x like the variable is, well, it's e to the x plus 2y. Okay, and then we need to evaluate at our bounds. Sorry, our upper bound is 2, not 1. Okay, so integral from 0 to 1 dy. And then let's plug in our bounds. And remember, we're plugging these in for x. So when we plug in 2, we get e to the 2 plus 2y minus, and then plug in 0, e to the 2y. All right. And now we can do our y integral. So this is going to give us 1/2 e to the 2 plus 2y minus 1/2 e to the 2y. And then we need to evaluate at 0 and 1. When we plug in 1, let's see, for this piece we get e to the 4, and then minus, actually we can factor this 1/2 out right away. So let's do that before we start plugging stuff in. So this 1/2 is now all the way outside. So plugging in our 1, we have e to the 4th minus e to the 2 times 1, so e squared, minus, and then plug in our 0. We get e to the 2 plus 0, so e squared, minus e to the 0, which is 1. Okay, and you can see either way we do get the same thing. We get 1/2 e to the 4th minus 2e squared plus 1, right, which is what we got when we did the integral in the other order. So that's kind of reassuring. That reinforces our intuition that if this double integral represents a volume, it should be the same volume either way.